Hi.
Hi.
All right. So how are you doing today?
I'm alright. How about you?
Pretty good. Pretty good. So basically to begin, I'm gonna show you a short clip. I'm not gonna tell you what it is, and after that we'll discuss. You ready?
Mm-hmm.
Oh, and before I start the clip, I wanted to let you know that the video has been silenced. There is a person in the back talking, but because this is to test your knowledge and to kind of gauge the experiment that we're going to be talking about, I've silenced the video.
Okay.
All right. You good to go?
Mm-hmm.
Okay. So I have a picture here.
Alright.
Thank you. Of what you just saw on the video, and I'm gonna give you about a minute to look at it, and then we'll discuss after that. You can just let me know when you're ready.
Okay.
All right. So after watching the video and then looking at this image of what you just saw in the video, can you tell me anything that you noticed, things that you realize, some prior knowledge that you might have, or any guesses?
So he was putting something in these wells. I'm not quite exactly sure what it was. But I'm assuming it's some sort of like liquid molecule or something. And then they were running a current through it because of the power source. And it seemed to be moving this way, like it says like the direction of movement. I'm not really quite sure what that movement means. And then like there's like bubbles in like the buffer solution, but I don't think that means anything. But other than that, I didn't notice anything else.
Okay. So could you tell me what kinds of things do you think biologists would be interested in putting in those sample wells? What did you think that you saw the guy putting in?
So like if they were maybe doing something like human related, maybe like an organic molecule, maybe like a protein, or like DNA, RNA maybe.
Anything else that they might put in there?
Blood.
Okay. That's an interesting one. Can you tell me why you said DNA or protein?
I'm just thinking like in terms of like maybe if they wanted to gain some more. I don't know how this would tell anything about DNA, RNA, but like if they're doing research, then like that's a primary thing that a lot of research labs are testing is like DNA, RNA, and like different species or different humans or stuff like that, because it can lead to a lot of new information.
And what kind of information do you think you could gain from testing DNA, RNA, or protein?
Think about it. Well, I'm assuming since they're like sort of running through a charge through, it's moving from negative to positive, maybe some sort of charge the DNA or something, or the RNA. Yeah, I don't know anything else other than that.
Okay, let's focus on DNA and RNA first. So you said that there's a negative and a positive charge. Could you tell me about how that relates to DNA?
Well, I know that like in DNA there's a lot of like hydrogen bonding and stuff, which is like sort of what helps to like keep it together. So maybe like a difference in charges in those bonds. Maybe like the other like some sort of like charged substituents attached to the DNA molecule that could probably help it move from negative to positive. Maybe like if a portion is more negatively charged than another one, then it might move further. I'm just guessing.
Okay. So you talked about the different bonds and interactions in DNA. Could you tell me how those bonds and interactions kind of relate to the overall charge of the DNA?
So I guess there's if there's like an overwhelming amount of negatively charged bonds, and that would sort of make the overall molecule DNA negative.
Okay.
Yeah, that's about it.
Okay. So basically you'd say that you were telling me that you'd put DNA or RNA samples in these wells. So based on how there's a difference in charges, could you tell me about what you think would happen once you loaded the DNA into those wells?
So if you put it in and then like in the video like he turned it on, like let's say if the DNA was negatively charged, like the negatives were going to repel from each other and then it's going to be attracted to the positive side. So it would, like in the video, probably move down this way. That's assuming that it was negatively charged.
Okay. Let's assume that it is negatively charged. Could you tell me why DNA would travel down?
We attracted the positive side.
Okay. What do you notice in addition to just, you see this negative sign here and this positive sign here, but let's say, I put, what else do you notice in this picture that could be responsible for DNA traveling down towards the positive side?
The current going through it.
Okay, and could you elaborate more on the current?
I guess if it's like starting from here and then possibly going through the gel, it would possibly charge the DNA, and then based on the fact that it was originally negative, it would move it over to the side.
Okay, so let's take a step back, and then you were talking about currents. Where do you think this whole apparatus gets its current from?
The power supply.
Okay, could you tell me more about what you noticed about the power supply?
It has two different attachments for where the positive and negative electrode go in, and then you can change the voltage.
Okay, and so what do you think changing the voltage, or how, for example, what if I put, what if I switched the electrodes and I made this one positive and this one negative? How would that affect if I was to load DNA in here?
Well, you said that DNA was negatively charged, and if it's already near the positive side, it probably wouldn't move.
Okay, good. So now that we talked about DNA, let's talk about something else that you mentioned that biologists would load in these sample wells, and that was protein, right? Why do you think biologists would want to load proteins into the sample wells?
Probably to help distinguish them from one another, because there's a lot of proteins. Yeah.
All right. Could you tell me something that you know about proteins, or anything that you know about proteins?
Yeah, there's obviously there's a lot of different proteins, and probably the fact that they're they might have the same basic structure, but there's obviously something in the protein that distinguishes it from one another. So some sort of group or substituent or something.
Okay, and do you know what that group or substituent is called?
No, I'm not sure.
Okay. So basically, you said DNA was negatively charged, right? What about protein? What do you think protein is?
I'm probably gonna assume that since there's a lot of them, that they could be all over the place. Some could be negative, positive.
Okay. And so what do you think, how do you think that relates to this apparatus that you're showing right here?
Well, if something was negatively charged, you could probably use the same apparatus. If something was positively charged, it probably wouldn't work, because what you said earlier, if we put the positive one here and the negative one here, it wouldn't work, because it'd be no way to move the molecule.
Okay, so that's interesting you say that, though, because when I told you that we switched, the electrodes and made this one positive and this one negative, you said that the DNA would just stay here. But now, when we, use the same apparatus, and this is negative and this is positive, you said that if we loaded a positively charged protein,
it wouldn't move.
wouldn't move, correct?
Yeah.
And that's because.
Well, if it's positive, well, if this one is negative and this one's positive, like they're gonna be attracted to each other.
Mm-hmm. Okay. Could you tell me something about maybe the difference in size between DNA and proteins?
DNA is much larger than a protein.
DNA is much larger?
Yeah.
Okay, if DNA is much larger, do you think it's going to want to, do you think it could travel easily?
Probably not.
Okay, so could you tell me, so you said that DNA would travel in this case. So if DNA does travel in a gel, what does that tell you of DNA size in relation to proteins?
The proteins would probably move faster if DNA does move, and it's so like, let's say it's really big and it does move. Then if proteins are a lot lighter, then they're obviously going to travel faster, or not faster, but they travel more in relation to DNA.
Okay. So let's take a step back, and you're talking about the different groups that a protein has, and how. Can you tell me something more about protein structure?
I remember there's like an amine group in the proteins, but I think like all proteins have that same basic structure. Probably like that different group in the protein, like it could be, besides being positive or negative, it could also be non-polar or polar.
Okay. So do you think that a protein just exists by itself in, like a single form, or do you think proteins are comprised of multiple structures of proteins?
Multiple, because like you have polypeptides.
Okay, exactly. So could you tell me something more about polypeptides?
It's like a combination of like a lot of different proteins, and they could have like different structures.
Mm-hmm.
I mean, they could be like globular, like circular shaped, and then like obviously like the different combinations of polypeptides could have a lot of different functions. And I guess in relation to this case, like it would vary, like the charges would vary if you have like a lot of different groups.
Exactly. So if the charges vary, what do you think that we might have to do beforehand, before we load the protein into the gel?
Charges varied. You probably have to make like an alteration to this apparatus, but I'm not quite sure what you would have to do.
Okay. So you said that proteins are negatively charged, so they can just travel straight down.
Yeah.
Right. But you said that, or DNA, is negatively charged, so it can travel straight down. But on the contrary, proteins can be positively charged or negatively charged. So because they have different charges, what do you think we might need to do in this situation before we load the protein into the gel?
I guess you might have to somehow identify if it was positive or negatively charged, and then like let's say you found out that it was negatively charged, then I guess you could use this. But if it was positive, then I guess you could flip it.
Okay. Say if we weren't allowed to flip it,
okay.
What do you think we'd want to do to the protein? If we weren't allowed to flip, the electrodes, what do you think we'd have to do to all proteins before we load them into the gel? Say we always want to do this to a protein before we load it into the gel.
Make them all the same charge, or like neutralize it?
Exactly. And could you tell me possibly why that is?
Why you would want to make them the same charge? I mean, like if you're saying like if you can't alter this apparatus, then if they're all the same charge, like negatively charged, then you could use this and gain more information about it. But if you couldn't do that, then it would be useless.
Exactly. So just to recap, could you give me a brief summary about what you learned about this apparatus, or a summary about DNA and proteins and this apparatus?
Sure. So you have both two electrodes, one negative, one positive. You have a current running from the negative to the positive side, going through the gel. You're going to load either DNA or proteins into these sample wells, and DNA is negatively charged, so it's going to want to move from the negative to the positive side. And the proteins, they could be either positive or negative, so you would want to make them the same charge, so you could still use this apparatus. And then you can alter the voltage on the power supply. And other than that, that's it.
Alright, thank you so much, man.
Yeah, no worries.
Alright.